Well, hello everyone. We are going to take a minute to talk about inverse functions, and this will probably be either an introduction to it for you, or maybe you've had a chance to talk about inverse functions a little bit in class, and now you're watching this piece, but we're going to just touch on kind of a variety of things as we look at these few problems here today. One of the things you need to know about inverse functions is the notation that we use. So we're just going to start with that. So if you have a function, f of x, the inverse of that function is f inverse of x. So this is not an exponent. This does not mean f of x is raised to the -1 as an exponent. This is notation for inverse, the inverse function. And one of the things that will happen with your inverse function with respect to your domain and a range is this piece of information right here. And this is going to be important to remember as we start talking about the domain of your original function and the range and how they kind of swap out. And the whole basis for this, and you'll see it as we look through some tables, is if you have your original function, and let's say you have numbers of, 0, 1, 2, and 3 for your x value, and then let's say you have numbers of, 11, 17, 23, and 29, okay? For your y value, or your function evaluated at x, what happens with the inverse is basically your x and y points reflect over the line y equals x. So what ends up happening is the x terms become the y terms, and the y terms become the x terms. So it would become, this would become 11, 17, 23, 29, and then the output of your inverse function would correspond to the previous x values in your original function. So one of the ways to deal with an inverse is to look at it in terms of a table. Okay, so we'll look at some tables when we work on inverse functions. Another way to look at inverse functions is to look at them with respect to their graph. So graphs of inverse functions are going to be the reflection of each other over the line y equals x. And then this idea of your domain and range is going to come into play as we talk about what makes a function an actual inverse. And one of the things that has to happen is you have to have what's called a one-to-one correspondence. So not only do you have to have one y value for every x value, but you also have to have one x value for every y value in order for the inverse function to be an actual function and not just a relation. Okay, so we're going to be talking about that a little bit more, how we can identify from our original function if it's going to be a one-to-one situation. And then also another layer that we're going to be looking at is how do you actually find the inverse of your function. So I want to take a look at these couple of equations that you see over here. And my recommendation is, and this is a great way to just start in creating your inverse, is to swap out your x and your y values. So we're going to interchange them, essentially. So we're going to end up with x is equal to 7y minus 9. And then we're going to solve for y right here. So we're going to be adding 9 and dividing by 7. So we're going to do a little mental math there, adding 9 to both sides, dividing by 7 to get y by itself. So now we have the inverse function, that is x plus 9 divided by 7, where our original function, our original f of x, was equal to 7x minus 9. And what happens, one of the definitions or ways you can tell that a function is an inverse of another, and this is going to become important for testing to see if one function is an inverse of another, is if you evaluate f of f inverse, you should get x after you simplify it all out. And also, if you evaluate f inverse f of x, you should also get it simplifying to be x. So some ways you can tell that a problem is going to be an inverse function. Okay, so let's try another one. We kind of have a tight grouping on our work here, so I'm going to go ahead and write that down if you need to write that down, because we're going to pause for a second here and erase this work so we have a little more space for our next example. Okay. Remember this piece. This is a good thing to write down, maybe in your notes or somewhere close by. All right. We'll figure out how to actually move that around one of these days. Okay, so let's take a look at this next. G of x is equal to 2 divided by x minus 5. I always just throw a y back in place of my function notation. It just helps me to remember that these are the two variables I'm going to be switching out. So I'm going to change this to x is equal to 2 over y minus 5. And this time, as I multiply both sides by y minus 5, hopefully that'll, y minus 5, stay on my screen there. What will happen is, give us a little more room here. These will cancel, and I am left with y minus 5 times x is equal to 2. So we'll go ahead and divide by x. Get y minus 5 is equal to 2 divided by x, and add 5. So we get y is equal to 2 over x plus 5. So you guys probably recognize this as a rational function, and it's going to have some kind of a vertical shift of 5 and an a value of 2. And if you look back over at this original function, probably recognize this one is going to have a horizontal shift and then still a stretch of 2. So they're very, very, very similar looking rational functions. And what we want to see, and you can try this in your graphing calculator, is if you graphed this function and then you graphed this function, that they should be the reflection of one another over this line y equals x, right here. That's what you should be seeing. Okay. All right, let's move on down a little bit here. I'm going to go ahead and skip over this example. I'm going to come right through here. One of the things to watch out for as we're finding inverse functions is it's possible that you might have to restrict the domain in order to have a one-to-one relationship or correspondence. Okay, and this is what I mean by that. When you have a graph like this one that we're about to take a look at, this 2x squared minus 5, it's going to be sort of a parabola that has a shift down 5. And as you imagine reflecting this over the line y equals x, what ends up happening is you end up having a situation where you actually don't have a function. Okay, so it would end up looking like this. Let's imagine if I were to reflect this point, you see me over here drawing on the graph over the line y equals x. If I were to reflect this point over the line y equals x, if I were to reflect this point and this point, what ends up happening is I get a graph that actually is not a function. It's a relation, but it's not a function. It does not pass the vertical line test. So this is not considered one-to-one. Kind of a tricky idea. So what we'll end up doing is we'll end up restricting the domain for some functions in order for their inverse to also be a function. And we'll talk about that in class a little bit more. But let's just go ahead and work through this process of switching out. Again, we're going to switch out our x and our y. This is how we're going to try to find our inverse function. We're going to add 5 and divide by 2. And here's where this becomes a problem. And you guys will see this happening. As I add 5 to both sides of my equation, here we go, plus 5 plus 5. All right, so we get x plus 5. And when I divide by 2, divide everything by 2, I have y squared is equal to x plus 5 divided by 2. So as I take the square root, part of the problem here is I'm going to get plus and minus. So I have this idea that my inverse function, for every value of x that I do plug in, I'm going to get 2 corresponding values of y rather than 1. And that's why we have to talk about restricting the domain. Okay, so that is the inverse function. Things like that would work, but again, this is why this happens. For every x value, now you're going to have 2 y values. So it's not one-to-one, and we got to be careful of that. So we'll talk about that a little bit more. This question, this example that you're about to see, is taken from your text. We only have about 3 more minutes available to us on this video. So let's just read through it together and just kind of talk about maybe what some of the expectations would be on a question like this so that you guys are ready for it when you see it in class. Is there a way to look at any graph to determine if its inverse will be a function? Find examples of other functions whose inverses are not functions. Well, just like we have the vertical line test, we also can use a horizontal line test to find out if a graph is going to have a function, an inverse that is a function. So if you imagine our parabola over here, and there's a lot going on with our parabola right now, so I'm going to use one more color. We'll see if I can change this up a little bit. And if you imagine taking a horizontal line and passing it through your original function, just like that, if that horizontal line touches your original function twice, then what will happen is the inverse will not be a function, right? And so it's, in order for it to have an inverse and have that one-to-one correspondence that we want, your original function has to pass both the vertical and the horizontal line test. So that's one way you can kind of double check it. How about this question number 8? A function is one-to-one when every element in the range corresponds to exactly one element in the domain. How does this help us determine if a function's inverse will also be a function? So again, if you swap out the numbers in your table and one of your x values goes to 2 y values, then it wouldn't be one-to-one. So analyzing a table might be a way to also see that idea of having it be one-to-one. This particular table is a graph of a linear function, and I went ahead and I'm just going to tell you what it is here real quick. Okay. And you would be able to find this out by using your graphing calculator or in a number of different ways. But one of the things we want to be able to do with our inverse function is to make a table for the inverse, determine how they're related, solve your new equation for y. So that's going to be swapping out those variables, right, and solving for y. So on this one, we're going to get y is equal to x plus 11 divided by 6. And then we would justify by, and I'm going to see if I can keep recording here just for one more minute, by seeing if f inverse of f of x is equal to x, and if f of f inverse is also equal to x. So that would be a way to justify your solution. Okay, that's all the time we have, guys. That was kind of a long video. Hopefully it went okay, and I'll see you soon.